So we will now move to the third presentation by Ronny LAUERWALD. So Ronny is a researcher at the University Paris-Saclay in the UMR ecosystem, and his research focuses on the impact of climate change on agricultural production and the contribution of agricultural activity to the anthropogenic greenhouse gas budget. Ronny, the floor is yours for 30 minutes.
So thank you very much for the introduction. So the topic of my talk is water requirements for soy self-sufficiency in the EU. This is a project on which I work, among others, with Nicola Gilpa and David Markowski. And those two, Nicola and David, they have been working on the possibility to increase the soil self-sufficiency in the EU. So what does that mean? So first of all, Europe uses a lot of soy, so mainly for animal feed. But like for the time being, or like this is a value that is valid for the period about nearly 10 years ago, the EU is producing itself only 10% of the soy that is consuming. So that's why the EU is a big importer of soy that's produced in other countries like in the US, but also in South America. And in South America, like these plantations for soy are expanding, and for the expansion of this soy cultivation, there's a lot of deforestation going on, and what has been sparked the debate about our responsibility for the destruction of nature in South America is, for instance, like in this example here on the right-hand side, the deforestation that is driven by the soy production that is again driven by our imports. And for example, like the Grand Chaco is a big dry forest area. There's a lot of deforestation going on. About 1/4 of that forest area has already been like destroyed and turned into either areas for soy cultivation or pastures. And so there's a demand to maybe reduce the importations of soy from these areas, not to drive this deforestation and this destruction of nature in these countries. So what is one reason to increase the soy sufficiency in the EU? Other reasons are, for instance, that if we produce soy in the EU, we can be more sure that it is not genetically modified soy. And it has also been shown that if you grow soy, because soy is one of these plants that fixes atmospheric nitrogen with the help of a little bacteria in the root zone, that you can also decrease like the nitrogen fertilizer application. So as I told you, Nicola, together with David, they have been working on that topic, and they have been conducting a study to predict the potential yield of soybean across Europe. So for this, they use machine learning to predict this potential soil yield based on different climate variables. So this soybean yield, this assumes only rain-fed conditions. And this is what you see here on the left-hand side. You have these predicted potential yields of soybean under rain-fed conditions given in tons per hectare. And on the right-hand side, you have a bit like the areas, this graph gives you the areas that would be needed to increase soy self-sufficiency and to attain a sufficiency of 50% or 100% respectively. So Nicola et al., they calculated that to reach soil sufficiency of 50%, you would need to cultivate soy on 4 to 5% of croplands. Here in the graph, I accidentally I switched that these two lines, so they should be switched. So it's the 4 to 5% of croplands that would be needed to reach 50% self-sufficiency. So this is valid for soils cultivated in 1 out of 3 years, and reach like 100% soil self-sufficiency. You would need to cultivate soy on 9 to 12% of the croplands in Europe. And so the big questions are, first of all, what kinds of crop you want to replace by soy to increase the soy self-sufficiency. And the other question is, because we are talking here about the water requirements, how would the cultivation of soy change these water requirements of crops? So how much more irrigation, or how much more would the yield depend on precipitation, and how much more irrigation might be necessary to further increase the yields? And so for our analysis, we started with the example that we want to take, maybe first consider replacing maize by soy. So why maize? Maize is one of the most important cultures in Europe. So in terms of cultivated area, I think it's like the third most important cereal after wheat and barley. And here we see, like, this is for the period 2000 to 2020, the average percentage of croplands on which maize or soy are grown. So we see that maize, this is a bit more widespread with the growth of maize. But you see we have some areas where especially a lot of maize is grown, like in the southern western part of France, northern Italy, like in the plains of the Po. And then you have large areas where maize is cultivated in Croatia, Hungary, and Romania. On the right-hand side, we see the distribution of areas where soy is cultivated. Here it's quite interesting that we see that actually it's also the cultivation, it's quite widespread, but only widespread in terms of like that there's at least some soy cultivated somewhere, but the proportion of soy is very low. So we see here that a little bit of soy is also cultivated across Germany, Poland, and even in the Baltic states. But you see here that most soy is cultivated in that you have an aggregation of soy fields in the northern part of Italy and in Croatia. So this slide gives a bit better overview about the present day soy cultivation here on the left-hand side. So here, first of all, we see that soy production has been strongly increasing over the last 10 years. So we see in the graph on the upper left that the production of soy has nearly tripled from 2012 to 2020. So in 2020, 2.6 megatons of soy were produced. And the countries that provided most to that soy production are Italy, that provide more than 1/3, followed by Romania, France. Then comes with similar contributions, Croatia, Austria, and Hungary. And here on the right-hand side, we see this is again the map, we predicted potential soil yield produced by Nicola and David. And here I've classified these areas according to minimum predicted soil yield, starting with 1.5 tons per hectare, then we have 2 tons per hectare, and then 2.5 tons per hectare. And so the idea is for the conversion of maybe maize to soy, we would preferably use areas where we projected soy yield is highest, so that we can minimize the area that needs to be converted to achieve maximum amount of additional soy yield. And for these three thresholds, we see the estimated results given in that little table on the lower right-hand side. So we see that if we take this very low threshold of 1.5 tons per hectare, we could have additionally nearly 17 megatons soy per year. And if we take a much higher threshold of 2.5 tons per hectare, so then the additional soy production is only 7.1. But I think, personally think that maybe like the middle threshold is quite reasonable trade-off. So if you take that, we would turn about half of these areas in Europe where maize is cultivated into soy cultivation. And then we could increase the soy production by about 30 megatons, which would mean that we more or less increase the overall or the present day soy production to the six-fold value, which would already be quite massive. But this is just some hypothetical example to develop our methodology. And so if we would take that threshold on 2 tons of soy per hectare and year. So the countries that would provide most to the increase in soy production would first of all be France, followed by Romania, Italy, and Hungary. So these 4 countries together, they would account for about 85% for that additional soy production that could be possible in the EU under rain-fed conditions. So now let's come to the question. So why do we care about the water requirements? So what we have here in that graph, this is like the water use in the EU. And we see here on the left-hand side, also on the right-hand side, we see like the water consumption by different sectors. And in green, we have the agricultural sector, and we see that on like the annual average, agriculture accounts for about 2/3 of the total water consumption. But if you move, or if you look at the graph here on the right-hand side, where you have this water consumption per quarter. So it's like each of these quarters is of course 3 months. And we see here that during the quarter 2 and 3, so this is the months from March, from April to October. And during this period, agriculture is actually really dominating the overall water use. And this is mainly because of water use for irrigation. And here in this graph on the left-hand side, we see the spatial distribution of irrigated cropland in the EU. Overall in the EU, like about 6% of croplands are irrigated. So in France, it's about 5%, so it's about on average. In Spain, it's much higher, so 16%. And Italy, it's just like even 33%. So to give some examples. And as I told you before, soy in particular is quite water demanding. And in France, although only 5% of the total area of the crop area is irrigated, the areas on which soy is cultivated in France, bit more than half of that area is actually equipped for irrigation because the soy is so water demanding. And in the upper right-hand side, you see what is called the so-called water footprint. So water footprint is the amount of water that is needed to produce that crop. That goes a bit hand in hand with the virtual water trade, what Raja was mentioning. And you see here in that list that, okay, we have 2 sources of water. We have a precipitation, which is also called like green water. And then we have what is called the blue water. This is coming from irrigation, the water taken from groundwater, from surface water to add to the fields because the precipitation is not enough. And we see here that water footprint is much higher for soy than for wheat and for maize. But this is also because like soy produces much lower yield than wheat or maize. So like for soy, it's what we have seen is like about 3 tons per hectares maximum, and for wheat in the EU under rainfed conditions, maybe something like 12 up to 12 tons per hectare, and for maize also about this value. But what we see here is that for the water what's consumed to produce soy, about 1/4 in France is coming, for instance, for irrigation. And for wheat, for instance, this fraction is really negligible. This is because most of the wheat is winter wheat, and this is not growing through the summer. It's already harvested early in the summer, so that during most of the period there's a little rainfall and there's a lot of evapotranspiration that wheat is not grown. But on the other hand, like soy and maize, these are plants that are like planted in spring and then grown over the summer and then harvested like end of summer or in autumn. And that's why here also like the contributions, these relative contributions of irrigations are much higher. And as we see here in this comparison, for soy, it's about 1/4 is coming for irrigation, and for
Ronny,
sorry, I didn't understand you.
no, I was just saying that don't worry about the signal. You can just continue, Ronny.
Okay. Yeah, I have to be a bit quicker. And so, yeah, so what we see here is a bit of comparison about the areas with a lot of irrigation and the areas where we have more or less renewable freshwater resources. And we see here that in many areas where we have a lot of irrigation, like in Spain, we have only little freshwater resources. So there cannot be more irrigation. But on the other hand, like for instance, in Italy, there's a lot of irrigation. You have also more freshwater resources, and where we simply irrigate a lot because we have these resources. And whereas here we were talking about Romania and Hungary as areas for more soybean cultivation, we see here that there's not so much renewable freshwater resources in those areas, but for the time being, there's also not so much irrigation going on. What we see here, this is a bit water exploitation index with water consumption relative to the amount of renewable freshwater resources. This gives like this index, and if you are at an index up around 20, then you know that these freshwater resources are already heavily under stress. And we see that is the case for Spain. But if you look at northern Italy, we have a lot of irrigation when we don't have a high water exploitation index, simply because there's a lot of fresh water. So where irrigation could further be expanded. But when you then look here, like in this big basin of the Danube that goes through Romania and Hungary, and you see that also this water exploitation is quite low. There's not so much renewable freshwater resources, but they already don't have at the moment a lot of irrigation going on. So let's now come to the question, how do we assess these crop water needs of soy versus maize so that we can use in our analysis? For that we use some model equations that were proposed by Allen et al. In 1998. So these are these guidelines to estimate water requirements and water needs from the FAO. So these are the guidelines that are used widely for planning, but also for different planning of different scales and farm scales to like for organizations that plan, I don't know, constructions of irrigation equipment. And it's also used a lot in research. So the estimation of these water requirements, these are based, first of all, on the so-called reference evapotranspiration. So we reference evapotranspiration is the evapotranspiration from a reference crop, and this reference crop is some sort of a perennial grassland that is well watered. So well watered means there's no water shortage, water limitation for the evapotranspiration, so that is equal the potential evapotranspiration. And for that, there's established physical-based equation, is called the Penman-Monteith equation, that calculates these estimates of these reference evapotranspiration based on temperature, net radiation, the soil heat flux, water pressure, and wind speed. So I don't want to go too much into details. And when what these method after Allen et al. Is based on so-called crop coefficients that help to transfer this potential or this reference evapotranspiration into a potential evapotranspiration that is crop specific. So you have specific Kc values for specific crops, not only for the crops, but also for different periods of crop growth. And so you have 4 periods. You have an initial period, so when the plants are like sown, and then when they are still little and only up to very like small coverage of plant, and then you have like development period when the plant grows massively, then you have a middle period when the plant gets more and more ripe, and then at the end you have the later stage, then you have a grain fill. And you see that KCB is like a factor to calculate from this reference evapotranspiration the potential transpiration. So this increases. So this is quite low. The initial phase where the plants are planted, then increases with other plant growth, is high during the middle stage of growth, and then decreases during the late stage, during the grain fill. And then you have KE, this is the coefficient that you need to calculate the evaporation, and that you see that you have like really the opposite pattern. So that is, of course, it's higher when the plant cover is smaller, and when it's lowest when the plant cover is highest. So you simply use these different equations to calculate like these crop-specific potential evapotranspiration during the growing season. And then finally you calculate based on these the adjusted evapotranspiration. This is like the estimate of the actual evapotranspiration, which further, or this is simply like the multiplication of these potential evaporation and transpiration times some correction factors that take into account how much soil moisture is there. So like for evaporation, you only have the soil moisture in the topsoil, and for like the transpiration, you take like the soil moisture over the whole root zone. And for that, you also estimate when the increase in the root depth over this growing period. So this is a bit how this model works. And this is some example how it works at the plot scale. So we have again here on the left-hand side, these are the different crop coefficients, and that lead to these potential evaporation and transpiration EC and TC. Then on the right-hand side, you see how when these actual evaporation and transpiration EA and TA are calculated based on like these potential values based on the root depth, so the area from which water can be taken out of the soil. And then you have, of course, also changes in the soil water storage. So to calculate these actual evapotranspiration, you need to keep track on how much water is in the soil. And what is quite important here is you see that in the early part of a year, so before like planting, you have an increase in soil water storage because there's not much evapotranspiration. Then after the plants grow and root depth gets deeper, and like the transpiration increases, then you have a significant decrease in the amount of water that is stored in the soil. And then after harvest, then the soil water storage is again replenished. And so how do we calculate the deficit? In evapotranspiration, for this we simply calculate the difference between potential evapotranspiration and the actual evapotranspiration. And this is about the gap in water availability that would reduce the yields because of water shortage. And this is the amount of water that you could, in theory, add by irrigation. So then how do we get to the European scale? To European scale, we simulated that over the period from 1999 to 2020 at a 25-kilometer resolution. And we have various regional to global scale data sets that you can use. So I don't want to go too much into details at this resolution. So these are the results for potential adjusted evapotranspiration and the deficit evapotranspiration for soy in the top row, maize in the bottom row. So these are the averages from 2001 to 2020. You see that generally the more south you get because of higher temperatures, the higher are the potential evapotranspiration. But if you look at the adjusted evapotranspiration, so this does not really follow the same pattern because this is limited by the availability of water. Here you see that in the south, you even have lesser adjusted evapotranspiration calculated than in like the central part of Europe. And then finally, you have then this picture for the ET deficit, that this deficit in evapotranspiration is of course highest in like the southern part of Europe and in particular in Spain, so where we have the highest potential but the lowest adjusted evapotranspiration. And to remind you, it would be that ET deficit that you would need to counterbalance by application of irrigation water. And yeah, but as we have shown you, like for especially for Spain, the amount of water, renewable freshwater resources that are available for irrigation are too low to actually apply that. So that's why much soy cultivation might not be possible, for instance, in Spain. So I think maybe we can quit this slide. We are a bit already behind the time. So what we see here is now how would the ET losses across EU change if maize was replaced by soy? So the ET losses with the adjusted evapotranspiration, so which is like the actual evapotranspiration, and we call it ET loss because this is the amount of precipitation that is lost back to the atmosphere that does not flow into the river and does not go into the groundwater, might there be useful for other purposes, so for other freshwater use. And so here on the upper left we see different. Yeah, so we see like the negative values, which would indicate that, does indicate that this water loss is lower if you plant soy instead of maize. And indeed, we see that over the whole Europe, on the right-hand side on the graphs, we have it summed up over the whole Europe. You see that you would, if you exchange maize by soy, you would even save some water. And the graph on the lower right, you see that this can be like you would save 1 to 2% of water, but relative to the evapotranspiration losses from maize, but it can be in some years up to 5%. But on the other side, this is maybe the last slide. Here we see this is how would the irrigation needs change. So the irrigation needs is like the difference. Here we look at the difference in the ET deficit. And like, again, if you have a negative value, it would mean that the deficit would be decreased with soy, but we have mainly positive values, which means that the irrigation needs would actually still increase. So it's an increase, if you look here in the lower right-hand side, increase by minimum 10%, but during some years it could range up to 25%. So which means although we can have the soy production under rain-fed conditions, there's still potential for more. And as David has shown, if you irrigate like soy or other plants, you get much higher yields. And so with water requirements, it could further increase soil production are much higher than you would have to increase maize production in the EU. So to quickly sum up, so much higher degree of self-sufficiency is achievable. It's even possible under rainfed conditions. So if you do it under rainfed conditions, you could even slightly increase at least like a groundwater renewable and what you save as renewable freshwater resources. But on the other hand, you would actually increase the irrigation needs. And this is something what you have to think about. Okay, so thank you very much.
Okay, thank you. Thank you very much, Ronny, for your presentation. We have time for one or two questions. Is there? You can. Yes, Raja?
I would like to have, I have a question, but I prefer if any other person from the participant
Okay.
have a question. Otherwise, I can.
No, I don't know if there are. No, you can go on, Raja, I think.
Okay. I was, thank you, Ronny, for your nice presentation. I was wondering whether maize and soy are a perfect substitute, because otherwise, if you replace maize by soy, and you still need to produce maize for other uses, not only for livestock feed. So then you will have the same problem. You will have the problem of indirect land use change, and you will have the same issue of imported deforestation and the same issues as you have actually with the soybean. Do you have an idea?
Yeah, I mean, you are of course perfectly right. So this is like what we did here, like using mice as an example. It's a bit more like a proof of a concept that our method is working. But of course, you cannot really like give up half of the areas where you produce mice, because of course you also need mice, and then you have the same problem. So what we want to do in futures, we want to look a bit more what kind of cultures could be replaced by soy. And then we can do the same simulations for different cultures, and then see also for the different cultures, okay, how does these water requirements change relative to that particular culture? And this is then also something that can help maybe in the decision which cultures should be replaced by soy. But of course, you should not only do it by mice. That's what was pretty a bit too much.
Okay, thank you, Ronny, for your answer. Did we have other question?
There is a question on the chat, Kamel. You can
Kamel, okay.
answer directly.
Oh yeah, I didn't see it. So Kamel, if you want to
yeah, in the same direction what Raja said. My question is really simple. Did you estimate by how much price and yield of soy today need to be increased that this crop become able to compete with wheat and maize? It's just roughly estimate. We don't, by how much we need to increase the price and yield of soya today to be able to compete with maize and wheat.
Okay, so we didn't yet take into account like these prices, but of course this is also something very important maybe to look at. So we didn't so far take that into account, but yeah, okay, really to make like these, because if you grow more soy and then have less of some other plants, you really would need to also look at to, yeah, what does it mean economically, and how does have maybe politics to help there with some substitutions.
Okay, thank you.
Okay, so maybe I have a last question. Did you compare your results to the situation in Argentina, so in the Gran Chaco, or even or in Brazil, so in the area of production in South America, to see whether the water requirements is differ from the situation in Europe. Because in fact, maybe just a bad idea to try to relocate the soybean production in Europe, because the production of cultivation are just better in South America.
Okay, I personally did not look at that, but yeah, maybe David can say something about that from his paper with Nicola. Is David still there?
Yes. About what? Sorry.
It's about have you compared in your paper with Nicola like these conditions for the growth, like climatic conditions for the growth of soy between like South America or like the US, where most soy is imported from, to Europe? Do we have similarly good climatic conditions to produce soy?
Yes, we have the answer, but I don't remember the answer actually.
Okay.
But indeed, we have calculated the yields of soybean at the global scale for different parts of the world. As far as I remember, the yields were higher in South America compared to what we could get in Europe. So I don't remember the difference, but indeed the conditions were better, the environmental conditions were better in Southern America than for Europe. But you have to keep in mind that a major factor impacting the potential yield of any crop, including soybean, is the selection of adapted cultivars. And so far in Europe, the investment in crop breeding is relatively low for soybean, because it's not a traditional crop in Europe. So we have a lot of investment for improving the cultivar of wheat, of maize in Europe. But for soybean so far, I think we still have some room for improving the potential yields by selecting cultivars adapted to European conditions. So I would say that if Europe decides to be more self-sufficient in soybean in the future, probably that more companies will invest for selecting better cultivars adapted to European conditions.
Okay, thank you very much, David, for your answer. Thank you, Ronny, for your presentation.